We know that gravity does far more than make things fall down. It governs the motion of planets around the Sun, holds galaxies together and determines the structure of the universe itself. We also recognize that gravity is one of the four fundamental forces of nature, along with electromagnetism, the weak force and the strong force. Gravity is by far the weakest force we know. If you pick up a book, you're counteracting the force of gravity from all of Earth. For comparison, the electric force between an electron and a proton inside an atom is roughly 1 quintillion times stronger than the gravitational attraction between them. In fact, gravity is so weak, we don't know exactly how weak it is. Unlike the force, with its dark and light sides, gravity has no duality, it only attracts, never repels. Tides are caused by the rotation of the Earth and the gravitational effects of the Moon and Sun. Gravity and weight are not the same thing. The force of gravity on an astronaut is about 90% of the force they would experience on Earth. However, astronauts are weightless, since weight is the force the ground exerts back on them on Earth. Because Mars has a lower gravity than Earth, a person weighing 75 kilograms on Earth would only weigh 28.4 kilograms on Mars. While Newton's older law of universal gravitation is accurate in most scenarios, modern physics uses Albert Einstein's general theory of relativity to describe gravity. Gravity makes waves that move at light speed. General relativity predicts gravitational waves. If you have two stars or white dwarfs or black holes locked in mutual orbit, they slowly get closer as gravitational waves carry energy away. In fact, Earth also emits gravitational waves as it orbits the Sun, but the energy loss is too tiny to notice. Gravity might be carried by massless particles called gravitons. In the Standard Model, particles interact with each other via other force-carrying particles. For example, the photon is the carrier of the electromagnetic force. The hypothetical particles for quantum gravity are gravitons, and we have some ideas of how they should work from general relativity. Like photons, gravitons are likely massless. If they had mass, experiments should have seen something, but it doesn't rule out a ridiculously tiny mass. Quantum gravity appears at the smallest length anything can be. Gravity is very weak, but the closer together two objects are, the stronger it becomes. Ultimately, it reaches the strength of the other forces at a very tiny distance known as the Planck length, many times smaller than the nucleus of an atom.